Welcome back. We're now starting the second module where we will talk about the control and data plane separation. By the end of the module, you should be able to explain the difference between the control and data planes, as well as the functions of each of them, including the infrastructure that's required to support each of the control and data plane. We'll also talk about the challenges of separating the control and data plane and various approaches that have been taken to tackling these challenges. The module comprises 3 lessons. The first lesson is the overview, where we'll discuss what control data plane separation is, why it's a good idea, and we'll provide a brief overview of the opportunities and challenges of separating the control and data plane. The second lesson will discuss opportunities in more detail, and the third will talk about challenges and approaches to tackling those challenges. So first, what are the control and data planes? The control plane is logic that controls the forwarding behavior in the network. Examples of the control plane are routing protocols, network middlebox configuration such as firewall configuration or load balancer configuration, and so forth. One can think of it in some ways as the brain of the network. The data plane, on the other hand, forwards traffic according to the control plane logic. Examples of data planes are IP forwarding, layer 2 switching, and so forth. The data plane is sometimes implemented in hardware, but also is increasingly implemented in things like software routers. So why separate the data plane and the control plane? One reason is that by separating the data plane and control plane, each can evolve and be developed independently. In particular, the software control of the network can evolve independently of the hardware. That means one can buy routers, switches, middle boxes, and so forth, deploy them in the network, and not be bound by the capabilities of software that ship with the hardware at that particular time. A second reason to separate the control and data planes is that it allows the network to be controlled from a single high-level software program. So higher order programs could control the behavior of the entire network. And in doing so, not only is it easier to reason about the behavior of the network, but it's also easier to debug and check this behavior. So there are various opportunities that we'll look at where separation actually helps. In this particular lecture, I will provide a brief overview of where separating the data and control plane can help in data centers and in routing. And in a subsequent lecture, we will talk about also where this control and data plane separation can help make certain applications in enterprise networks easier to manage. We'll also talk about how the separation of control and data plane can help in research networks by allowing research networks to coexist with production networks on the same physical infrastructure. One particular domain where separating the control and data planes has proved particularly useful is the data center, where it's relatively commonplace to need to move a virtual machine from one physical location in the data center to another as traffic demands shift. As one example, Yahoo cites that it has about 20,000 servers in a cluster in a data center, resulting in about 400,000 virtual machines, each of which might need to communicate with any other virtual machine, thus resulting in about 1,024 distinct interhost links between any pair of virtual machines for the topology that they've deployed. Now, if on top of that you want to guarantee sub-second virtual machine migration and guaranteed consistency in the network as that migration occurs, this problem becomes particularly hairy. The solution to this problem that Yahoo has taken is to program each of the network switches from a central database. So as virtual machines migrate, that central controller knows about the migration and can update the switch state accordingly so that network paths update in accordance with the virtual machine migration. As another example, suppose that an attacker is sending denial of service attack traffic to a victim. In this case, it can sometimes be difficult to squelch that traffic near the source. One approach that AT&T has taken is to separate the data plane, or the routers that forward that traffic, from the control plane that makes decisions about what to do with particular traffic flows. In particular, they've deployed something called the IRSCP, which is a commercial version of the RCP, which we've talked about. which will insert a null route into a router for particular flows or destinations that are receiving attack traffic. So those are just two examples of how the control and data plane separation have helped in specific cases, but there are also challenges to making the control and data plane separation a reality. The first is scalability. Once you separate the control elements from the forwarding elements, it's likely that a control element may be responsible for many forwarding elements and sometimes thousands of forwarding elements. The other challenge is reliability or security. What happens if a controller fails or is compromised? Well, we should hope that the forwarding elements continue forwarding traffic, business as usual. But once we've separated the brains of the network from the devices that are actually forwarding the traffic, correct behavior is no longer guaranteed if a controller should fail or be compromised. So in the coming two lessons, we'll talk about both the opportunities and challenges associated with separating the data and control planes. We're continuing our discussion of the benefits of control and data plane separation. And in this lesson, we'll talk about the opportunities from control and data plane separation in terms of two examples. One is new routing services in the wide area in terms of maintenance, egress selection, and security. And the second is benefits in data center networks in terms of cost and management. So to remind you, this module has 3 lessons. We covered the overview last time, and in this lesson we will talk about opportunities in various domains that exist as a result of control and data plane separation. We'll then talk about some of the challenges and approaches to addressing those challenges for the control and data plane separation. So let's jump into the first example, which is benefits of control and data plane separation in the wide area. So if you know anything about interdomain routing, or perhaps you remember it from your undergraduate networking course, you may remember that policies, or ways to set policies in interdomain routing protocols, are very constrained. Today's interdomain routing protocol, the Border Gateway Protocol, or BGP, artificially constrains routes that any particular router in the network can select. That's because route selection is based on a fixed set of steps, and there are a limited number of knobs to control inbound and outbound traffic. It's also very difficult to incorporate other information, such as auxiliary information about the reputation of a route, time of day, and so forth. The separation of the control and data plane makes it a lot easier to select routes based on a much richer set of policies, because the route controller can directly update the state in the forwarding plane independently of whatever software or other technology may be running on the forwarding elements or the routers and switches themselves. So let's look at a few examples. One example is called maintenance dryout. The idea here is that a network operator may want to do planned maintenance on an edge router. So in this example, let's suppose that the operator wants to do maintenance on the router sitting at egress 1. In this particular example, the operator could use something like the RCP, or the routing control platform, to directly tell a router at ingress to send its traffic for a particular destination to egress 2. This would be much more difficult in today's networks because the network operator would have to use existing routing protocols to adjust the configuration of individual routers in the network to effectively tell all of them to switch their route from one egress point to another. This could be done in a lot of ways, most likely in tuning the intra-domain weights, for example the OSPF weights, on each individual router. But that's a very indirect way of doing this. It's much more direct to have a controller directly tell the router which egress point to use. The second example would be to let customers themselves control the selection of egress routers. So for example, if a particular customer wanted to use one data center or another to reach its particular services, Again, the network could use the RCP to send traffic for one customer to one data center and another customer to a different data center. This would, by contrast, this would be very difficult in today's networks because BGP is routing traffic based on destination prefix. So if a particular service was served from a particular destination prefix, all of the traffic, regardless of customer, would go to the same data center. In this particular case, the RCP could route traffic to different data centers depending on the source, in particular, in this case, depending on which customer the traffic was originating from. As another example, we could imagine how separating the data in control planes could result in better security for interdomain routing. So while there are secure routing protocols that exist, many of them are very difficult to deploy. There are also auxiliary monitoring systems that can tell an autonomous system about the reputation or potential security or insecurities of a route advertisement, but there's no way to directly incorporate that information into BGP or interdomain route selection. So one idea might be to use an existing anomaly detection system to detect suspicious or bogus routes and to prefer familiar routes over unfamiliar routes. So if a particular autonomous system learned two routes to a destination D, one of which looked suspicious and the other which did not, the control plane, or an RCP for example, could tell the routers in that autonomous system to all prefer routing to that destination via the preferred route. By contrast, this would be very difficult to do in today's networks because there's no easy way to incorporate reputation information into the route selection process. Another area where the separation of the control and data planes can significantly benefit network operators is in data centers, and in particular, this separation can drastically reduce the cost of running a data center. Looking at a typical data center with about 20,000 servers and a fan out of 20 in the data center topology, we see that the requirements to support this topology is about 10,000 switches. If we take a particular switch from a standard vendor that costs $5,000, we're now talking about the cost of about $50 million just to deploy the switches. If, on the other hand, we could deploy commodity switches based on merchant silicon that cost only about $1,000, now we're talking about a switch deployment cost of about $10 million. So if we're talking about a large service provider that has 10 data centers, maybe a Google or a Yahoo or a Facebook, now we're talking about a savings of $400 million, which presumably you could use then to hire engineers to develop control systems for controlling those commodity switches. The benefits of that separate control result in more flexibility, the ability to tailor the network for specific services, and the ability to quickly improve and innovate, because as we've noted, once the control plane is separate from the data plane, it is a lot easier to control the behavior of the network because those switches are doing nothing more than just forwarding traffic, and all the smarts of the network are in the software control. Let's take a look in particular at how separation of data and control plane can make it easier to manage a data center through more flexible control in the context of addressing. So let's suppose that you have a data center with tens of thousands of servers and you want to figure out how you should address those servers. On one hand, you could use layer 2 addressing like Ethernet. This results obviously in less configuration or administration because if you've got one large layer 2 Ethernet, you can essentially just plug everything in and it's a flat topology. On the other hand, a flat topology with tens of thousands of servers clearly results in poor scaling because these layer 2 networks are typically broadcast. On the other hand, we could do a layer 3 network, and the benefits here are that we could use existing routing protocols and scaling properties are much better, but the administration overhead is a lot higher because we have to configure these routing protocols. For example, if we're using an intra-domain routing protocol like OSPF, then the network operator needs to configure the link weights and the topology and adjust those link weights accordingly to load balance traffic, account for failures, and so forth. So on the one hand, there are some conveniences to using layer 3 addressing or topology-specific addressing like IP, but there are also some drawbacks like higher administration overhead. So how do we get the best of both worlds? Well, one idea is basically to use layer 2 addressing and construct a large layer 2 network, but to make those addresses topology specific rather than topology independent. And how we do that, because MAC addresses are typically flat. Well, the idea basically is we can use MAC addresses, but we can renumber or readdress these hosts so that the addresses of these hosts have MAC addresses that depend on where they are in this topology. Now, hosts can still send traffic to the other hosts' IP addresses in this data center topology, but the problem is that since we've reassigned the MAC addresses in the topology to be topology dependent, the hosts don't actually know that they've had their MAC addresses reassigned. They still think that they have their old flat MAC addresses. So, as we know, if a particular host wants to send traffic to another host's IP address, it will use the address resolution protocol, or ARP, to send out a broadcast query that asks who has a particular IP address. In other words, what is the MAC address for this particular IP address that I would like to send to? And the trick here is that we don't want the host, the destination host, to respond because it still thinks it has its old MAC address. What we can do in this case, because we have separate network control, is to use something called a fabric manager or a separate controller to basically intercept all of these ARP queries or all these queries that are wanting to discover MAC addresses for particular IP addresses. So when this particular switch receives a query that says, tell me the MAC address for a particular IP address, that switch can kick that query to a central controller or a fabric manager, which can then reply with the topology-dependent pseudo-MAC or PMAC. And then all of the traffic can be rewritten with the appropriate source and destination topology-dependent MAC addresses. So that's just one example of how a separate controller in a data center can allow a network administrator to get the best of both worlds in terms of both topology dependence and the benefits of a layer 2 topology. We'll look at data centers a lot more in a particular module where we look at case studies of SDN later in the course. But this hopefully gives you a flavor of the types of benefits that separating control and data plane in a network can offer to network operators and administrators. There are a number of other opportunities that the separation of the control and data plane can offer to network administrators. For example, here at Georgia Tech, we're looking at how the separation of control and data plane can enable dynamic access control for campus and enterprise networks. And there are another number of other opportunities that you can see here listed out, many of which we will explore throughout the rest of the course. You can also check out the URL below here on the OpenFlow site to look at various videos that explore different case studies of how the separation of data and control plane can make network management and operations easier. Welcome back to the course on software-defined networking. In this lesson, we're continuing our discussion of the control and data plane separation, and in particular, we're talking about the challenges associated with separating the data and control planes. We'll overview several challenges associated with the separation of the control and data plane, including scalability, reliability, and consistency. And we'll talk about approaches to solving these problems in the form of two different systems, the routing control platform and ONIX. Let's first take a look at some of the scalability challenges faced by the routing control platform and the approaches that that platform takes to solving some of these scalability challenges. So one of the problems that the RCP faces is that it must store routes and compute routing decisions for every router across the autonomous system. And a single autonomous system may have hundreds to thousands of routers. So that's potentially many routing tables and a lot of routing computations all being performed at a single node, whereas before all those computations were distributed across the routers themselves. So some scalability principles from the RCP design. The first is to eliminate redundancy. So rather than storing a routing table for every single router in the autonomous system, the RCP stores a single copy of each route, and if those routes are duplicated across the routers in the autonomous system, as is commonly the case, that redundancy can be represented by storing pointers into a common data structure. The second principle is to accelerate lookups by maintaining indexes to identify the particular routers that may be affected by a change in network conditions, such as the advertisement of a new route or a node or link failure. Therefore, when a particular event happens, the RCP only needs to compute new routing information or routing tables for the routers that are affected by that change, rather than recomputing the state for the entire network. Finally, RCP tackles some scalability problems by simply punting on performing routing for all the routing protocols in the network and simply decides to focus on performing interdomain routing alone. The ONIX network controller applies a couple of related principles to handle scalability problems. The first is partitioning, whereby an ONIX controller might actually only keep track of a subset of the overall network information base or network state in the network, and then apply various consistency protocols to maintain consistency across different partitions. The ONIX controller takes advantage of two different consistency models. One is a strong consistency model that ensures that different replicas are strongly consistent at the expense of some performance. The other is a weaker consistency model that is more efficient about passing information around more quickly. The second scalability principle is aggregation. So the ONIX design essentially describes the notion of a hierarchical set of controllers, such as, for example, having an ONIX controller for a department or a building across a larger enterprise network, and having a single super ONIX controller that effectively controls those subcontrollers for the overall domain. Let's now take a look at how these systems tackle a second challenge, that of reliability. So one particular approach to reliability is to simply replicate. So the RCP design advocates having a hot spare, whereby multiple identical RCP servers essentially run in parallel, and the backup or standby RCP could take over in the event that the primary fails. So the idea here is that the network would run independent replicas of the RCP, whereby each replica has its own feed of the routes from all the routers in the autonomous system. Now, if each replica receives the exact same inputs and runs the exact same routing algorithm, then it should be the case that the output or the resulting state that each of these RCPs would push back into the routers should be exactly the same because the inputs and the algorithm are exactly the same. So in the case of the hot spare approach, there's actually no need for a consistency protocol if both replicas always see the same information. There are potential consistency problems, however, if different replicas see different information. Let's see how that might be the case. So here are two RCPs. Let's suppose that they see different information and as a result compute different outcomes or desired routing table state for routers A and B in this autonomous system. So the RCP on the left might compute an egress route for router A that says use egress router D to reach a particular destination, and hence use router B as the next hop to reach the egress router D. Now similarly, the second RCP, the RCP on the right, might install conflicting state into router B that says use egress router C to reach that destination and use A as the next hop to reach the egress router C. Now you can see that if these two replicas install this respective state into routers A and B, then we have a forwarding loop between router A and router B, because in trying to reach that destination, router A is going to use the gold route to try to egress via router D, and router B is going to use the gray route to try to egress via router C. And when each of these routers receives the packets for that destination from its respective neighbor, it's just going to bounce the packets back and forth. So what we want is for route assignments to be consistent even in the presence of failures and partitions. Now we previously just said that if every RCP receives the same inputs and runs the same algorithm, then the output should be consistent. So we want some way to guarantee that. Now fortunately, a flooding-based internal gateway protocol, such as OSPF or ISIS, as we've learned in our networking course, essentially means that each one of these replicas already knows which partitions it's connected to, because if the RCP is participating in the intra-domain routing protocol, or the IGP, then it sees the full link state of that partition. And that information that it receives is enough to make sure that the RCP only computes routing table information or routing state for the routers in the partition for which it's connected. And that alone is enough to guarantee correctness. Let's see why. Let's suppose that we have a network partition where the routers in partition 1 can't see or can't forward traffic to the routers in partition 2, and vice versa. Now in this case, the solution would be to have that single RCP only use state from the routers in each one of these partitions in assigning routes. For example, to assign routes to routers in partition 1, the RCP would only use the set of candidate routes that it learned from the routers in partition 1. It would not use any candidate routes from routers it learned from partition 2. And that alone is actually sufficient to guarantee consistent forwarding. You can intuitively see why, because for example, if the RCP never assigned a route learned from partition 2 to a router in partition 1, then effectively partition 1 and partition 2 are simply just acting as independent networks with a common routing control platform. Let's suppose now that we've got multiple RCPs, that we've actually replicated the RCP, but the network itself has multiple partitions. Now here you might think that we've got a more serious problem, because you might have cases where there are partitions that are reachable by both RCPs or can be seen by both RCPs, but you have others that are reachable only by subsets that may be non-overlapping. Well, the approach here is to just ensure that the RCPs receive the same state from each partition that they can reach. So the IGP provides complete visibility and connectivity for each of these partitions. And if the RCP only acts on a partition, if it has the complete state for that partition, then it's guaranteed that the routes it assigns for that partition will be consistent. In other words, there'll be no forwarding loops. Let's look now at how ONIX tackles the challenges of reliability. So ONIX talks about different types of failures that may occur in the network. The first is network failures. In this case, ONIX simply just assumes that it is the application's responsibility to detect and recover from those failures. Now, if a network failure affects reachability to ONIX, the design suggests that the use of a reliable protocol or multipath routing or so forth could help ensure that the ONIX controller remains reachable even in the case of a network failure. Now, if ONIX itself fails, the solution is to take a similar approach, which is to apply replication and then use a distributed coordination protocol amongst those replicas. Now, because ONIX has been designed for a far more general set of applications than the routing control platform, a more complicated distributed coordination protocol is necessary. Some of the details of those coordination protocols are discussed in the paper that was referenced on the original slide where we introduced ONIX in this lecture. So, in summary, separating the control and data plane poses three significant challenges. One is scalability. In particular, a single controller must now make routing decisions or various control plane decisions on behalf of many network elements that were previously each performing those computations independently for themselves. The second challenge is reliability, that is, guaranteeing correct operation under failure of the network or failure of the controller itself. The third challenge is consistency, or ensuring consistency across multiple controller replicas, particularly in cases of network partitions or failures. So we explored each of these challenges in some detail and talked about various techniques including hierarchy, aggregation, and various clever state management and distribution that various systems such as the RCP and ONIX have used to tackle these challenges. Each particular controller tackles these challenges in a different way, but many of these principles apply across different controller designs and implementations.